Welcome to the Technical Education Series program on Basic Electronics. Today, we are going to discuss on bipolar junction transistors. Let us start with a question. What is a transistor? The word transistor itself will give the answer for the question. Transistor is a combination of transfer and resistor. And transistor is a device which transforms current flow from a low resistance path to the high resistance path. It's a three-terminal semiconductor device most commonly using in all kind of electronic equipments. The first demonstration of the transistor is in the year 1947 by Bell Laboratories, New Jersey. And three individuals were credited with the demonstration of the transistor, that is John Burdeen, William Shockley, and Walter Brattain. The most common application of the transistor is as an amplifier, but it can also be used for other applications such as oscillator, modulator, wave shaping, and switching circuits. Different types of transistors are in use, such as bipolar junction transistors, BJT, field effect transistors, FET, unijunction transistors, UJT, and so on. But our discussion is limited on bipolar junction transistors. Bipolar junction transistor is a three-terminal active device consisting of two PN junctions connected back to back in a fashion of either NPN or PNP. Since the current flow inside this transistor is caused by two opposite polarities of charge carriers, holes and electrons, this transistor is more appropriately called bipolar junction transistors, BJT. As BJT is made of N-type semiconductor and P-type semiconductor, and it is also consisting of PN junction, it is better to have a review on N-type semiconductor, P-type semiconductor, and PN junction before further discussion on bipolar junction transistors. Now let us see what is N-type and P-type semiconductors. As we know, N-type semiconductor is a semiconductor doped with a pentavalent impurity atom consisting of electrons being the majority carriers and equal number of positive ions created as a result of donating electrons at the time of doping, and few thermally generated holes being the minority carriers. In the case of P-type semiconductor, it's a semiconductor doped with a trivalent impurity atom and consisting holes being the majority carriers and equal number of immobile negative ions created as a result of accepting electrons during the time of doping, and few thermally generated electrons being the minority carriers. PN junction. We have seen what is N-type semiconductor and what is P-type semiconductor. N-type semiconductors and P-type semiconductors by themselves are of little use. But when a P-type semiconductor is suitably joined to an N-type semiconductor, a PN junction is formed. This PN junction is the basic building block of all the semiconductor devices used in the electronic equipment. While forming a PN junction, the most important thing is the action taken place at the moment they form a PN junction. And we will see that. Suppose this is the moment just before the formation of the junction, and we will explain what is going to be happen at the time of forming a junction. At the moment when a junction is formed, current carriers, particularly from the area near to the junction, will start to diffuse, so that electrons from the N region will diffuse to the P region and holes from the P region will diffuse to the N region. The electrons diffused to the P region will combine with the holes available in the P region. Similar way, holes diffused to the N region will combine with that of the electrons available in the N region. When an electron is combining with a hole, suppose if this particular electron is diffused and it is combined with this particular hole, this atom will become negative ion. Similar way, when a particular hole is combined with the electron, that atom will become positive ion. As a result of few such electron-hole combination, a row of positive ions are appearing near the junction in the N region and a row of negative ions are appearing near the junction in the P region. And this is the action. Let's listen. Now, a row of positive ions are formed near the junction in the N region and a row of negative ions are in the P region near the junction. Here, a narrow region of fixed positive charges are formed in the N region and a narrow region of fixed negative charges are formed in the P region. And this region is called space charge region or depletion region. Due to the presence of this depletion region, further diffusion of charge carriers will be prevented. That is, when an electron is trying to cross the junction, the negative charge in the P region will repel back the electrons to the N region. Similarly, when a hole trying to cross the junction, this positive charge will repel hole back to the P region. So that electrons in the N region and holes in the P regions are depleted to both sides. Thus, a potential barrier is set up against further movement of charge carriers and is called potential barrier or junction barrier. This junction barrier will have the same effect as we are connecting an external battery as positive to the N-type material and negative to the P-type material. Potential barrier for the silicon will be 0.7 volt and germanium will be 0.3 volt. Now let us see the PN junction in different bias state. PN junction with zero bias means when no voltage is applied across the junction, PN junction exists with a depletion region of normal in size as it is at the time of formation. If an external voltage is applied across the PN junction in such a way as negative to the N-type semiconductor and positive to the P-type, the junction is said to be in forward bias. At this time, the negative terminal of the battery repels the electrons in the N region and positive terminal of the battery repels the holes in the region, so that the holes and electrons will move towards the junction and reduces the depletion layer. And if the external voltage exceeds than the junction barrier voltage, current carriers crosses the junction and current flows through the PN junction. And if the PN junction is applied with an external voltage of polarity as positive to the N-type semiconductor and negative to the P-type semiconductor, the junction is said to be in reverse bias. In this case, the positive terminal of the battery attracts the electrons from the N region, whereas negative terminal of the battery attracts holes from the P region, so that both holes and electrons will move away from the junction, so that the depletion layer will be widened. And in this case, there will be no current flow through the junction. But if there is any minority carriers are there, they can cross the junction and will produce a small current through the junction and is called leakage current. Now let us start the structure of BJT. Bipolar junction transistors can be structured in two different ways as NPN and PNP. If a thin layer of P-type semiconductor is sandwiched between two N-type semiconductors, the resulting structure is called NPN transistor. In a similar way, if a thin layer of N-type semiconductor is sandwiched between two P-type semiconductors, the resulting structure is called PNP transistor. In both cases, the left region of the structure is called emitter, and the middle region is called base, and the right region is called collector. And the symbol of the NPN transistor and the PNP transistor are shown. In the symbol, you can see an arrow mark in the emitter lead of both transistors. It actually indicates the direction of conventional current, or we can say the direction of the whole current. In this structure, the collector region is the largest in size, and the emitter region is smaller than collector, and the base region is the smallest region. But in case of emitter, it is heavily doped region, and the collector doping density is less than that of emitter, and the base is very lightly doped region. The function of the emitter is to inject the current carriers to the collector via base. And the function of the base region is to pass the current carriers from the base and also control the current carriers. And the collector is actually meant to collect the current carriers from the emitter. Let us see the table. Here the size of the emitter is more than base but less than the collector. Size of the base is small than both collector and emitter, and the size of the collector is more than emitter and base. The doping density, emitter is heavily doped, base is less than emitter and collector, and the doping density of the collector is between heavily doped emitter and lightly doped base. And the function of the emitter is emit current carriers to the collector via base, and the function of the base is to pass and control the flow of carriers, and the collector is meant to collect the injected carriers from the emitter. Unbiased transistor. When no voltage is applied between the different terminals of the transistor, that transistor is said to be in unbiased state. And this is the unbiased state of an NPN transistor. As we know, a transistor consists of two junctions, that is emitter base junction and the collector base junction. At the time of construction of the transistor, depletion layers will be formed on both junctions of the transistor. Here it is the depletion layer formed in the emitter base junction, and this is the depletion layer formed on collector base junction. In a depletion layer formed on a junction, the number of impurity ions will be equal on both sides of the junction, so that the extension of the depletion layer will be more into the lightly doped region than that of the heavily doped region. Since the emitter is heavily doped than base and collector, the depletion region formed in the emitter junction will be smaller than that of the depletion layer formed on the collector junction. In the depletion layer formed on the emitter junction, the extension of the depletion layer would be more into the base since it is lightly doped than that of the emitter. In the similar way, the extension of the depletion layer in the collector junction will be more into the base region as it is lightly doped than that of the collector. Let us conclude. Extension of depletion region will be more into the lightly doped region to include equal number of ions on each side of the junction. As emitter is heavily doped than the collector, the depletion layer width at the emitter junction is smaller than depletion layer width at the collector junction. Depletion region at emitter junction extends less to the heavily doped emitter and extends more into the base region. Depletion region at collector junction extends less into heavily doped collector and extends more into the base. Operating regions of the transistor. As we know, a transistor consists of two junctions as emitter junction and collector junction inside it. And each junction of the transistor can be set in two different states as forward bias and reverse bias. Accordingly, a transistor can be operated in four different regions based on the bias state on both junctions as first state reverse biased on emitter junction and reverse biased on collector junction. So the region of operation is cut off. And the second case is forward bias on emitter junction and reverse bias on collector junction. And the region of operation is active and it is the most commonly operating region of the transistor. And third case is forward bias on emitter junction and forward bias on collector junction so that the transistor is operating in saturation region. And the fourth case is reverse bias on emitter junction and forward bias on collector junction. In this state, the transistor operates in inverse action. Operation of NPN transistor. This is the setup for the operation of NPN transistor. You know, in the case of NPN transistor, the emitter region is made of N-type semiconductor so that it is having electrons being the current carriers. The base region is made of P-type semiconductor and the size of the base region is very small so that it is having only few number of holes being the current carriers. The collector is again N-type semiconductor and it is having electrons as the current carriers. For the normal operation of the transistor, we have to provide forward bias across the emitter junction and reverse bias across the collector junction. Here, the forward bias across the emitter junction is provided using battery VEE and reverse bias across the collector junction is provided using battery VCC. The forward bias applied across the emitter junction reduces the depletion region at the junction and causes electrons in the emitter to cross over to the base region and holes available in the base region to cross over to the emitter region. This movement of majority carriers, that is movement of electrons from the emitter to the base and the flow of holes from base to emitter will constitute the emitter current IE in the transistor. Out of the electrons arriving at the base from the emitter, only few number of electrons, nearly less than 5%, will combine with the holes available in the base region and constitute a small current through the base lead called base current. With respect to p-type base, the electrons from the emitter are being treated as minority carriers. These minority carriers can very simply pass through the collector junction since it is reverse biased, so that the rest of the electrons from the emitter will cross the collector junction and pass through the collector lead to constitute the collector current IC. So we'll conclude the operation of NPN transistor as electrons traveling from emitter to base and few holes passing from base to emitter together will constitute the emitter current IE. And electrons flowing through the base lead as a result of recombination with the holes at the base constitute the base current IB. Electrons arrived at the collector and flowing through the collector constitute the collector current IC. Operation of PNP transistor. This is the setup for the operation of PNP transistor. The operation of PNP transistor is in the similar way as that of the NPN transistor, but the direction of the current will be opposite in PNP transistor. In case of a PNP transistor, the emitter is made of p-type semiconductor and it is having holes being the current carriers, and the base region is made of n-type semiconductor and the size of the base is very small, so that it is having only few number of electrons being the current carriers. Again, collector is made of p-type semiconductor having holes being the current carriers. Here the forward bias across the emitter junction is provided using battery VE, and reverse bias across the collector junction is provided using battery VCC. On application of forward bias across the emitter junction, majority carriers will diffuse the junction, that is, holes from the emitter will diffuse to the base region and the electrons in the base will diffuse to the P region. As a result of this charge movement, that is due to the flow of holes from emitter to the base and the movement of electrons from base to the emitter region will constitute the emitter current IE. Out of the holes arriving at the base region, few of the holes will combine with that of the electrons available in the base region and constitute a small current through the base called base current IB. The rest of the electrons, now they are appearing as minority carriers with respect to the base, will cross through the reverse biased collector junction and causes to have an electron flow through the collector circuit and constitute a current called collector current IC. Let us summarize the operation, that is holes traveling from emitter to base and few electrons passing from the base to the emitter together will constitute the emitter current IE. Then holes recombining with the electrons at the base causes electron flow through the base lead and constitute base current IB. Holes arrived at the collector causes electron flow through the collector and constitute collector current IC.